third day of this workshop, and we start today with a talk by Holmes talking about robust statistical decisions and the model misspecification.
Thank you. Thank you to the organisers for the invite to speak to you today. Thank you to the audience for turning up for the first talk after the conference dinner. I appreciate it. So this is going to be a fairly kind of gentle talk about a piece of applied methodology that has arisen out of applying Bayesian methods in applications in biomedical genetics, which is an area that I work in. So I have a joint appointment between the Department of Statistics at Oxford and the Wellcome Trust Centre for Human Genetics. This work I'm going to talk about today is joint work with a PhD student of mine, James Watson. So just to give you a bit of background to this, so one of my main research interests is in computational decision theory, particularly in the context of applications in what we would say modern biomedical genetics. So we've seen over the last 10 years or so, the cost and the availability of high throughput sequencing of DNA and RNA, for example, has dropped faster than kind of Moore's law. And so now we're in a position, certainly over the next 5 to 10 years, we'll be doing routine sequencing of almost every individual that's coming through the National Health Service in the UK. And so in the applications of statistics, we arise certain questions like whether to treat a patient with a particular drug, say, based on their genetic profile. So can we use information contained in DNA to help predict which patients will respond to which treatment and which ones won't, or which treatment to put a particular patient on? And so there's two kind of fairly large studies that I'm involved in. One is the Mainstream in Cancer Genetics study that's funded by the Institute of Cancer Research out of the Royal Marsden, which is probably the UK's leading cancer hospital, where we're looking at inherited DNA, so-called germline variants. So these are genetic variants that you would have inherited from your mother and your father. And for patients presenting with breast and ovarian cancer, at a certain number of positions on the genome, we want to say, look, if you carry this particular genetic variant, do you respond better to a particular treatment or not, or what is your risk? So this project here I'm involved in is looking at inherited genetic variation in your genome, and there's another project I'm involved in on the Health Innovation Challenge Fund Award, looking at leukemia patients, or rather a subtype of leukemia patients, and there we're looking at genetic variation that occurs somatically within the tumor. But the question is the same, is if we sequence the tumor or the cancerous cells, can it tell us something? Can it be informative for which treatment you go on to? And so of course this is a decision problem, and so questions that arise when we start to build these kind of big models on large scale data is increasingly we have to find, and this is the kind of the basis of this conference or workshop, is we need computational and statistical shortcuts in order to streamline the analysis due to the kind of the data that we're faced with. And so this talk is really about applying Monte Carlo methods to kind of formally and systematically examine the stability of decisions to model in assumptions. Okay, so that is, you've done your best possible, you've really tried hard, you built your best possible model under your current constraints. Yeah, and so that model informs you on the decision, but what's the stability of that decision? If you'd made a slightly different, if you'd chosen a slightly different likelihood function, or a slightly different prior, or used a different computational method, would your decision have changed radically? And so it's really about the stability of statistical conclusions. It's formally written up, this work, in a paper which we put recently on the archive. Okay, so a bit more, background. So in order to address the increasing complexities of modern data analysis, perhaps so-called big data, we've seen a kind of a rise in the development and use of approximate models. So I've just listed off a few, things like INLA, composite likelihoods, ABC, variational Bayes, And the kind of interesting aspect here is that these models are misspecified by design. Okay, so you know going into the analysis that these models are somehow some proxy for used for kind of computational constraints and statistical constraints. So here I'm going to use misspecified to mean that the model that you actually use differs from some hypothetical notion of a true model that you would have used, given infinite compute time and kind of infinite time for internal subjective elicitation. Okay, so there's a notion of a true model, best model, and then there's the model that you actually use in practice, say by doing Monte Carlo sampling with an approximate likelihood, etc. Okay. So, of course, decision analysis is one key application area of statistical data analysis. I'm interested in questions such as whether to treat a patient with a particular drug, but equally in finance, whether you should buy some stock or not, or whether you should gather more data, experimental design. These are all decision problems. But, of course, if the statistical models are approximations, then so are the resulting decisions. So an often cited strength of Bayesian statistics, of the Bayesian approach, is that it somehow systematically accommodates uncertainty in parameter values and in model structures, kind of model choice issues via joint distributions on the unknowns. Okay, but I'm interested in that kind of external part to all of that. Yeah. So what about the stability to kind of extrinsic ex post uncertainty? So you've done your best possible thing, but you're still concerned. Yeah, you've had to make some kind of modeling assumptions. Okay, and just to note, this is more for like students, that Bayesian statistics, formally assumes that the true model is contained under the support of your prior. Yeah, and we often, as Bayesian statistics, we say we say we like it because we're coherent, etc. But that only holds if you have the true model, or if you believe you hold the true model within the support of your prior, and all bets are off otherwise. There's a branch of Bayesian statistics that deals with M-open issues that concerns us. Okay, so within a conventional kind of Bayesian analysis, we will often use Monte Carlo approaches to compute the expected reward of a particular action. And then we'll choose the action that gives us the greatest expected reward. Okay. So that is, let A denote an action, say to treat a patient with a particular drug, given partial information, say their DNA, their genome in X, and a model. Okay? And so simply speaking, we generate samples, or we use MCMC to generate samples from our posterior distribution. So I'm going to use this to denote pi sub I will denote your current best subjective beliefs about the unknown state of the world theta that enter into your reward or loss function R. Okay, so conventionally pi sub I would be your posterior distribution of theta given X, but it could be slightly more general than that. Okay. And so I'm going to write this, or you can see that this is really a weighted average here with uniform weights on each of the samples drawn from pi sub I. So of course this Monte Carlo, MCMC, we're going to generate these theta i's, we're going to plug them into our loss function, we're going to take an average with weights 1 over n, and then we're going to choose the action A, which gives us the highest expected reward. And what I'm going to argue today is that it's interesting to explore retrospective reweighting. Okay. That is, we're going to explore how by using either resampling these weights according to some strategy or resetting the weights deterministically, we're able to make formal statements about the decision robustness that has arisen from all of the kind of layers of model approximation that have entered into the use of this as your model. Okay. So informally, when I talk or communicate with non-statisticians, one idea of thinking about this is like shaking your model, yeah, a little bit. So you've put all of your effort into generating this pi sub I, your model for unknown state theta, and then the external things you just want to kind of shake it a bit, and by shaking it I mean by changing these weights. Okay, and I think you can see is that, you know, if I perturb the weight slightly and the utility changes greatly, then it might suggest that there's some instability in the decision process, or some instability might arise for small change in weights if my decision, my optimal decision or action changes radically. Okay, so just some notation. So theta is going to denote the unknown state of my world, my so-called savage small world. So that is, theta is the unknown states that are going to enter into my loss function. Okay, A, I'm going to assume a finite set of possible actions that we are wishing to choose between. L is going to denote a real valued loss function which arises when taking action A, when nature really turns out to be in state theta. And from the previous slide, this is just, the loss is, of course, is just the negative utility or negative reward. Okay, and as I said before, pi sub I theta is just going to be my model, your best possible model under all of the constraints, computational constraints and learning constraints. And just to note, of course, that if you knew the state of the world theta, then the decision is solved. Yeah? You just choose the action which gives you lowest loss or highest reward. Okay. And so where Bayesian decision theory comes in, of course, is when there's uncertainty in the state of the world, pi theta, and hence uncertainty in which is the optimal action. So if you have perfect trust in your model, then we know what to do. Yeah? Following Savage's work in the 50s, we know that optimal decisions should be taken by minimizing expected loss or maximizing expected utility. That is, in a world where everybody behaves perfectly coherently, it is as if they were taking actions according to the principles of minimizing their expected loss. And as we've seen, this can be just sort of a weighted average, weighted by your beliefs in the probability of the event. Okay. The difficulty with Savage, of course, and general Bayesian decision theory is that it relies on a joint model to infinite precision. So you have to assume that you have some known likelihood for the observations x given theta and some known prior. And if either of those is not true, then there's a question of what does the posterior actually represent. Yeah? So kind of formally it represents the posterior beliefs of somebody who really believes the likelihood and who really believes the prior, who really does believe in this object here. But you don't, because you've just specified those for, you know, for computational reasons or for modeling reasons. Okay, and so again, how can I trust decisions if I'm going to plug this object into this integral? Okay, so Savage and Bayesian analysis assumes kind of a perfect trust in your model. And there's another extreme which arrives out of Wald's work in taking minimax decisions. So in the absence of any model, Wald considered a kind of a game theoretic approach following the work of von Neumann and Morgenstein, where he said, let's treat decisions under uncertainty as a zero-sum two-person game against nature. Okay. In which case, you should select your action to kind of minimize the worst possible thing that nature could throw at you. So the zero sum means that whatever you lose, nature gains, and whatever nature gains, you lose. Yeah. Okay. And the game aspect of it is that nature's going to be playing maliciously against you. Okay. So it's kind of strange. So it's akin to nature kind of reactively selecting the worst possible distribution function for you. You select your action, and then it's as if nature would put a Dirac function on the state of the world theta, which gave you the maximum loss. Okay. So whilst kind of interesting in its construction, it's really not applicable. It makes no, a person that followed Minimax would be a very weird. You protect yourself, you'd never get out of bed in the morning, or so it's a very there's not many kind of applications of it. Okay, so these really represent kind of two extreme positions. Wald assumes nothing, and assumes that nature's going to play against you. Savage, in some sense, assumes everything. Okay, so these are two extreme positions, as I said. So Savage assumes perfect knowledge, Wald assumes nothing. And so I'm just going to use a cartoon to say, let M here denote the space of all possible model distributions. Okay, and so we're going to take this Savage, your Bayesian model sits here. It's a point in model space, and somewhere out here is the other point in model space, which represents by Wald, which is this Dirac on the worst possible outcome. Okay, so there's been interesting work in the robust control literature and econometrics literature about trying to kind of soften or bridge these two positions. So following others, and there's a very good monograph book by Hansen and Sargent. So Hansen, who's the recent Nobel laureate in economics, has a series of papers on robust decision making in economics. And the approach that they and others have adopted is the following. It really kind of was driven by original work by Whittle in signal processing, in robust control. Is that consider the Bayesian model, pi I, as a useful but as an approximate reference model. So you're not going to put all of your, you're not going to hang kind of your beliefs that this is the true model here. But it's useful, but it's approximate. And what they say is we're going to investigate the Wald minimax distribution, but constrained to be within some neighborhood, some ball of models around pi I. Okay. And so we're going to construct a neighborhood around your model in model space, and we're going to search for the worst possible thing that can happen, i.e. the minimax distribution constrained to lie within this neighborhood defined by some divergence gamma, and with a radius of the ball defined by C. And so C really kind of gives you your trust region. How much do you really trust your model? If you trust it infinitely, you'd set C to 0. If you trust it not at all, you'd set C to infinite, and you would recover, of course, the Wald. Okay. So our local minimax distribution is then going to be defined as this constrained minimax. So we're going to find the distribution within gamma. And gamma here is centered on your kind of Bayesian model. In particular, so to define gamma, this neighborhood, we're going to need a divergence measure or some criteria of distance between distributions. And in particular, as we'll show later on, or as we show in our paper, Kullback-Leibler is really the only distribution function you can use. Well, it's the only one that gives you coherency. Okay. So we're going to define this neighborhood according to a Kullback-Leibler neighborhood around around the Bayesian model pi I. And so Kullback-Leibler isn't symmetric, so we need to look at the way we define this. So this neighborhood is defined with respect to the unknown model pi of theta. So it's the distance, so it's the divergence of pi I, the model that you're using, from the unknown, say, minimax distribution. So I said that Hansen and Whittle have kind of developed this in a number of papers, but specifically for dynamic linear models that arise in econometrics and in signal processing, so i.e. aka Kalman filters. So for dynamic linear models, they showed that you can get these things in closed form. But here, in the work with my student James, is we show that there's a simple way to derive the general form of this local minimax distribution under any probability model. And the form of it is quite, it's very simple and perhaps intuitive. So here we are. So what we're trying to do is we're trying to find the distribution function centered around your model with the constraint that it lies within some Kullback-Leibler divergence of distance or divergence measure C, and that maximizes your expected loss. Okay. So what we show in the paper is that the local minimax distribution has this very simple form. Okay. That it looks like this exponential tilting of the original Bayes model. So here's your Bayes model. You're going to exponentially tilt it by the loss function, yeah, and everything, of course, just needs to be normalized. Where lambda here is a non-negative real-valued scalar that's monotone in C. Yeah? So the bigger that C gets, the bigger lambda gets. And what you can see is the larger lambda gets, the more this distribution function is going to concentrate around the outcomes theta, which maximize your loss. Okay, so the simple proof that we have in the paper just follows from noting that this minimization problem or maximization problem here has a minimization problem with a Lagrange dual. Okay, so we can write this arg sup as this arg inf, where we look at the expected utility plus some penalty now, yeah, on the Kullback-Leibler divergence. Okay, so just to note, again, this is more, I guess, for students, is that this thing looks like a kind of a standard regularization problem. So you have a cost function that you're trying to minimize plus a penalty, or a cost function you're trying to maximize plus a penalty. Yeah? And so it looks like a kind of a penalized regression type problem, but it's on the space of probability measures. Yeah? So you might have seen something similar to this like in the lasso or ridge regression, where you try and find a value of theta which maximizes some cost subject to some penalty. Here we're doing the similar thing, but over distribution functions. Okay. Well, if you look at what this thing is, this is an expectation with respect to pi, and this is an expectation with respect to pi. So just writing those things out, we have these two integrals, both with respect to pi, just gather in terms. It's very simple just to see that it has this following form. Okay. Just to denote that this form, this general form for any kind of model, has been derived kind of independently in the following two papers, but using more general but more technical results using exponential families and large deviation theory. Okay, so just some comments on what this this minimax distribution looks like. As I said, it looks like an exponentially tilted density. So if you take a linear loss function, so the loss is just some a theta, then that local minimax is something that's, say, well known. I'd never heard of it, but it's known as the Escher transform that's used in option pricing and actuarial science. So lambda here, as I said, is the kind of confidence in your model. If you really believe your model, you set that neighborhood to 0 and you get back to Savage, your standard Bayesian approach. If you set that lambda equals to infinity, then you have no trust in your model and you're playing this kind of minimax game, and so you get back to Wald. The other thing to note is you expand that neighborhood out, your minimax distribution will lie on the shell of this ball, of this Kullback-Leibler ball. So the Kullback-Leibler divergence between the local distribution, the local minimax, and your model will be C. It's unique by strict convexity of Kullback-Leibler divergence, and by symmetry, if you were actually seeking the best possible outcome, and we'll see an example of why you might want to do that. So if rather than seeking the worst possible thing that could happen within this neighborhood, if you were to seek the best possible thing that would happen, again you just have this exponential tilting, but here we have a negative term. So in other words, you're putting values that reward you for taking the action. These are just some results from playing around with this. Perhaps this one is the thing to note, is that this Kullback-Leibler divergence that's set between your minimax, local minimax distribution and your original model is kind of bounded by the difference in the two expected losses. So clearly the expected loss under your kind of minimax is going to be higher than the expected loss under your Bayes model, because that's the thing we're maximizing against, subject to this constraint, and it's bounded by that kind of neighborhood size. Okay, so in the original papers by Whittle and in the work by Hansen and Sargent, they make a strong claim for why you should use Kullback-Leibler. You know, there's lots of reasons why Kullback-Leibler is the natural kind of divergence measure to use in defining this ball, this neighborhood, that arise from kind of information theory and invariance. But in a paper with James, what we do is, I think it's quite nice, is we show that actually the Kullback-Leibler divergence is unique in being the only coherent divergence criteria one can use to define this neighborhood. And I'm not going to go through it. I'll point you to the proof in our paper. It's adapted from a proof that I have in a paper with Stephen Walker and Bissery. Yeah. And what do I mean by coherent? I mean that if I take a data set of size n and a prior model, for coherence we mean that that if I give you, suppose somebody on this side of the room starts off with the same prior model as somebody on this side of the room. So they have the same prior model. I'm going to give them the same data, it's just I'm going to give the person here all of the data. I'm going to give the person here some portion of the data, they're going to update, and then I'm going to give them another portion of the data, and they're going to update again. Now for coherency, we would want these two people to end up with the same result. Okay. So for coherency, formally we want that the local minimax distribution updated using with a portion of the data, and then the likelihood for the next portion is the same for any partition of the data as being given all of the data and just updated in one shot. And what we show is the Kullback-Leibler divergence is the only divergence criteria that meets that. Okay. So conceptually, you know, if you think about this just a little bit, you can see, well, actually we could put this constraint on a priori before you've observed the data. Okay. That is, you know, rather than thinking about these local minimax distributions occurring a posteriori, what we could do is define a local minimax kind of robust prior. So we could take your original prior that you started with when you were about to update and do your Bayes learning, and we could exponentially tilt it and then also update this distribution here using the standard likelihood. Okay, so how does this relate back into Monte Carlo? Well, just very kind of simply is that, of course, if your model is approximated by a bag of samples generated by some kind of Monte Carlo scheme, then using the above, it's very simple to evaluate this local minimax expected loss using a deterministic reweighting. Okay, so rather than taking the original weights, which were just 1 over m, say, for the samples theta I drawn from your model, what we can do is we can reweight them by this exponential loss. And this reweighting is deterministic. And of course, you can also recover the form of that, use Monte Carlo methods to recover the form of that minimax, what that local minimax distribution looks like. Okay. So clearly, if lambda is very big, then this estimator is going to be really poor. We know that. Okay. And so you might want to use something, let's say, like a sequential Monte Carlo, something that actually looks to update not just the weights but also the atoms as you move. But formally, I mean, lambda large is less of an issue because hopefully you've done a pretty good job in specifying your original model. So that kind of cartoon is a bit kind of misleading. What we want to do is we're really thinking about small neighborhoods here. Yeah, if you're confident in your modeling approach, yeah, this neighborhood should be in some sense small, and therefore the lambda is small, and therefore this kind of exponential tilting, the Monte Carlo estimator from that exponential reweighting will not have kind of too high variance. Okay, so I wanted to go through for the local minimax just a couple of kind of examples, kind of canonical examples, just to get a feeling for what this does. So let's just look at generically at prediction. So what happens if we're doing prediction under this scheme? So I'm going to assume that you, as the modeler, has been asked to provide a predictive distribution for some future outcome y given x. So this is in a regression model setting. Okay. And so what's the loss function in order to report your best beliefs, your best kind of beliefs about this predictive distribution? Well, following, Bernardo and Smith, local and using a local proper scoring rule, the appropriate loss is the kind of the log information, or the log likelihood, yeah? The log of the probability distribution. Note the kind of scoring rules are designed to keep Bayesians honest, yeah? In terms of how they rank preferences. So in providing a predictive distribution, your loss function is going to be the log kind of predictive loss. So if you really believe your model, as in if you're in the standard kind of Bayesian approach, well, of course, your honest beliefs say that you report your predictive distribution is just going to be the marginal distribution under the model space. Yeah? So you would just marginalize out of all the things that you don't know about theta that enter into the predictive and just report that. However, of course, there's two things here. Yeah? So first of all, it assumes that the model is correct, which, is the basis of the talk. There's another thing, I think, which is particularly interesting in biomedical, kind of currently in biomedical research, and more generally in kind of like big data, is this notion that's in data mining they call concept drift, whereas statisticians we might call ascertainment bias, which is that your training data, the distribution function or the population distribution of your training data is never the same, yeah, as your predictive data. Yeah, that is patients change. Yeah, the world is changing. Of course, the world is changing. Yeah, all around us. Yeah, but when we gather a set of samples to build a model, yeah, the distribution of how those samples arise is never the same distribution as the one that we're going to be predicting on. So there's two errors we might kind of concern ourselves in this. Firstly, it assumes you've got the true model. Secondly, in some sense, it assumes that the data you're predicting on is the same, has the same kind of form or distribution as the data that you trained on. Okay. Well, what happens if we plug this into this local minimax solution? We get the following. Yeah. So we're going to tilt it by the negative loss, which here is the log self-information, and so we get this following form. I.e., we're going to get this tempered distribution. We get this 1 minus lambda form. I.e., we're going to take, what it says is that you should take your original prediction that you're going to do, and you should kind of heat it up slightly. That is, you should, smooth the modes in your predictive and fatten the tails. So this kind of notion of predictive tempering arises under this idea of model misspecification naturally as a kind of a local minimax. I.e., you should only report pi y given x if you really believe your model. Okay. For time, I don't want to go into this. So this just, next two slides just says that actually there's a form of things called Gibbs posteriors, which myself and others have recently worked on, and again, they can be naturally interpreted within this framework. Okay, so as Bayesians, or as people doing Bayesian statistics, we're used to kind of averaging out over unknowns. Okay, And so again, a kind of very natural question is, well, if you have some trust region around pi I, why not consider the distribution of expected losses that arise from other models within this neighborhood? So rather than just calculating the expected loss for the particular model you've got, why not explore, losses that arise from other models that might have been, true within this neighborhood? Okay, so it turns out that it's very hard, or we couldn't kind of think of a natural way of doing this with the Kullback-Leibler divergence defined as, pi I from pi. But if you change it to the other way, then there's a method to move forward. So we're going to do a change of neighborhood now. So now the Kullback-Leibler divergence is with respect to the expectation under your model. Okay. So interestingly, we no longer have the analytic form for the local minimax distribution. However, there is a very kind of simple, well, fairly simple Monte Carlo approach for calculating the variation of expected loss over all distribution functions within that ball, centered around the model. Okay. So we're trying to take expectations over distributions within the neighborhood of pi I. That's we need a probability distribution on probability measures within that ball. And that is classically a problem in Bayesian nonparametrics. But here we want to put like a nonparametric prior centered on a posterior distribution. And so the natural workhorse in Bayesian nonparametrics is the Dirichlet process from Ferguson 73, and it's where we started, and in some sense it took us all the way to where we wanted to go. Okay, so the obvious thing to do is to, using a Dirichlet process, is to center the Dirichlet process on your model and then draw samples according to some concentration parameter alpha. Okay. So in some sense, this distribution is centered on your model. The larger alpha gets, the higher the concentration, the tighter that pi, the samples will be, loosely, around pi I. Okay, so, in practice, the Dirichlet process is via this, really has a generative form. Okay, which follows this simple thing, which is first of all draw samples theta I from pi I, your baseline measure, and then weight them according to draws from this Dirichlet, which which is symmetric with parameters alpha over m, and take m to infinity. Yeah. So do an infinite or an increasingly large number of draws from your baseline measure, and then draw these weights from this symmetric Dirichlet. Of course, so we thought about this, and then we said, okay, so if one does that, what is the divergence of pi tilde to pi I? Yeah, because we wanted to stay within the Kullback-Leibler, so we said, okay, so we draw this pi tilde, now what's its divergence measure to pi? And of course it's not defined, because, in fact, it's not defined between any two draws, because they don't have common support, because you draw the pi I from you draw the thetas from pi I, and so they don't have common support, and therefore the Kullback-Leibler isn't defined. So we're going to introduce just a simple trick here of developing coupled Dirichlet processes. Okay. So I'm going to define a coupled Dirichlet process in the following way. So we say that two or more Dirichlet processes are coupled if in the following way. If they have a common baseline measure, pi 0, but they can have different concentration parameters. Okay. But the constructive definition is that they share the same atoms. So I'm going to draw now pi s from the baseline measure, but I'm going to independently reweight the samples from independent draws from the Dirichlets. Okay. And take m to infinity. Okay. So it's important to say that these are coupled, but asymptotically they're independent, because the draws of the draws of the weights are independent. But given two realizations, of course, because they have common support, the Kullback-Leibler is well defined. And it takes the following form. It's just the expected, as we would kind of see from here, it's just the expected log ratio of the weights. Okay, so this is now nice. It now allows me to define some Kullback-Leibler representation or divergence between any two draws. Okay, so then the natural thing now is to consider one of those draws to have infinite concentration. Yeah. So I'm going to set the concentration parameter to be infinite for one of those draws, and of course I get back what looks like a Monte Carlo representation of my original distribution. i.e., if I draw theta I from pi I and I draw a Dirichlet, a symmetric Dirichlet with an infinite parameter, this will just set this to be 1 over m. But by coupling one of the draws with a concentration parameter infinity from pi I and the other one with some alpha, we'll get this following Kullback-Leibler divergence between the draw of pi star and the draw from pi I, which has this infinite concentration. And it has the following form. Okay. So we can see that this Kullback-Leibler divergence measure is itself a random variable because these weights are random. The weights that you drew for the pi star, which has concentration parameter alpha, this has random weights from the Dirichlet. So it's a random variable, so we can look at, well, what's the distribution of this Kullback-Leibler divergence of this draw. To do so, we look at the kind of the representation of the Dirichlet as a normalized sum of gammas. So the way that we can generate the weights for Wi to be Dirichlet is you draw for each Wi, you draw a gamma random variable with parameter alpha and 1, and then you just normalize. Okay. And then if we take m to infinity and let capital G denote the sum, i.e. the denominator here, of these random variables, then we see that G also follows a gamma random variable. Yeah? So the sum of the gammas is gamma. Under this representation, we have the Kullback-Leibler divergence for a draw from the Dirichlet process from its baseline measure as represented by this symmetric draw, this coupled Dirichlet process, but with an infinite concentration parameter, has the following form. So the Kullback-Leibler divergence of pi tilde from its baseline measure just has the form of the log of this gamma function here minus 1 over m times the sum minus m. And this is what I'm really kind of getting to, is that from the properties of the gamma random variables, what you see is that when you draw from this Dirichlet process, it actually sits on the shell of a Kullback-Leibler ball of fixed radius, i.e. there's no diversity in the Dirichlet process with respect to the Kullback-Leibler divergence from its baseline measure. So in other words, that this radius c is given by log alpha minus the digamma function of alpha, where alpha was your concentration parameter in your Dirichlet process. i.e., and I've not seen this before, but in some sense when people use Bayes nonparametrics and sample from the Dirichlet process with a fixed concentration parameter alpha, you're actually only exploring a very particular part of the distribution space, i.e. a model space of Kullback-Leibler divergence of fixed distance. It's kind of, I mean, again, for students, it's analogous to this kind of well-known result for the multivariate Gaussian. Yeah, so if you draw x from an independent multivariate Gaussian in high dimensions, if you take p large and then look at like the L2 norm of x, the draw, it actually just concentrates in a very thin shell. So i.e. almost the entire measure is contained in a thin shell of radius sigma root p. It's a kind of it's an analogous thing here that's happening for the Dirichlet process. Okay, so this makes our life easy because all we now have to do in order to draw distribution functions constrained to be within a fixed ball is draw the radius up to some constant c, and then draw the Dirichlet, draw a sample from the Dirichlet process. So, to recap, what I'm saying here is that we can retrospectively use Monte Carlo samples from your original model, your kind of baseline model, to explore sensitivity to model misspecification and hence robustness of decisions by reweighting your samples. So the original Monte Carlo, as I said, we just have this kind of weighting where these weights are 1 over m. We can find the local minimax distribution, the worst possible thing that could happen to you under a particular action, subject to this kind of trust constraint that the Kullback-Leibler divergence between the minimax distribution and your model is less than c. So it's deterministically reweight your samples. We can also use coupled Dirichlet processes to say, if we're interested in building a neighborhood centered at pi I, yeah, but constrained to be within some neighborhood C, Kullback-Leibler divergence C, we can just stochastically reweight your Monte Carlo samples. Just kind of shake, this is the idea of shake your model. You just kind of add a bit of noise onto your weights. But by adding noise in this particular way, we're able to make some very kind of strong statements about what you're sampling from. Yeah? Okay, so maybe the last 5 minutes. So here's a case study taken from the literature for screening design. So this is a kind of, just give you a sense of how we could use this. And it's for breast cancer, it's public health policy for screening breast cancer patients. So many countries in the world operate a kind of a breast cancer screening policy where women over a certain age will present to a clinic for samples to look at potential for cancerous tissue, for breast cancer. Okay. So a primary issue in determining this optimal kind of screening schedule is first of all choosing a starting time t0, which is the age of the first screen when women should first present, as well as frequency delta for subsequent screens. How often should people represent, should return for screening? And this kind of model was looked at by Parmigiani in '93, who proposed using a semi-Markov process. So the model is kind of pretty simple here. We've got a 4-state semi-Markov process where individuals start off in state A, that's disease-free. At some time point, random time point TB, they progress into what's a preclinical stage. Okay, so this would be asymptomatic breast cancer. So these are the people in this stage that you hope to pick up from your screening policy. Okay. These people here can either go on to a clinical stage, so where breast cancer is being picked up, yeah, or into an absorbing state death here. And of course people can also can not get breast cancer, but of course everybody dies, yeah, at some point. Okay. And so in building a kind of, in carefully kind of building the Bayesian model, the decision process is we want to optimize the intervention, yeah, the time at which we take people into preclinical screening. We need to build models, of course, for these distributions, yeah. We need to build likelihoods, okay. And following Parmigiani, they use these kind of these forms, log normal forms and a Weibull form for time to kind of death. And an individual is kind of characterized by this kind of triple, yeah, by their path through that Markov process. Okay, so with this model set up, we can easily write MCMC. We did this. We drew 10,000 samples from the posterior distribution to fit in this model here, yeah. And then using the fitted model or the Bayesian model, we can then explore different screening policies to look at their consequences. Okay, the loss function, again, this is kind of an illustrative example, has a very simple form here. We're going to take a very simple form where each screen is going to cost you R. Yeah, where R is a kind of a relative cost for screening relative to picking up an individual at the preclinical stage. So R trades off the cost of one screen against the cost incurred by the onset of the clinical disease. And following Parmigiani, we take R to be, 10 to the minus 3. Okay. So here's our model. Here's your kind of, in some sense, your best Bayesian model. We have a distribution of transition times across from A to B, B to C, as well as the overall lifetime distributions of individuals here, and a histogram of the losses that are occurred at the optimal. When you look over the optimal possible screening design here, it says that the first present at age 40 and then re-present yourself every 3/4, I think it's over 10 years. Okay. But of course that assumes that the model is true. So can we play this kind of stability analysis by taking these Monte Carlo samples and reweighting them? So initially we can reweight them deterministically and look at what happens to local minimax losses. So how good is this screening design if we perturb the model slightly? Yeah. So does this screening policy look very bad if you just perturb the model a little bit, or is it stable? Okay. So we looked at 12 potential different schedules, screening schedules, starting from patient initially presents at age 40, comes back, every 9 months, up to presents at age 50 and returns every 15 months. And we can look at the distribution of their expected losses under those different schedules, and of course the optimal screen has the lowest expected loss. But if we look at what happens within a kind of a local minimax distribution, what we can see is that here's the difference in expected loss between these screens. So the flat line here is comparing the best screen, if you really believed your model, against all other screens. Yeah? And so you can see screens which originally look worse, suddenly look better here and then look worse, but this one here looks systematically better as you grow this Kullback-Leibler divergence. Okay. In particular, the change in optimality occurs with the Kullback-Leibler radius greater than 5.5. Scheduled 1 now looks best. Okay. Well, what does that mean? A kind of Kullback-Leibler of 5.5. Well, again, because we've reweighted the Monte Carlo samples, we can explore what the marginal distributions look like. And so if we look at what happens here, actually this slide will be better, is that for the initial optimal model assumes that the transition times between preclinical and non-clinical follow this red distribution. But if you've got that wrong, and actually those transition times are much shorter, then that particular schedule looks poor. Okay. Again, we can use the Dirichlet process sampler to explore variation in loss within a local ball, and we see again that there's some instability occurring. Okay, so just to summarize, we've used Monte Carlo methods to formally explore decision stability in the absence of a true model. We've shown that deterministic reweighting using this kind of local minimax leads to predictive tempering, and we show that Kullback-Leibler is the only coherent measure. Stochastic reweighting using coupled Dirichlet processes allows you to sample from the space of distributions within a ball. So my final kind of conclusion slide is this is the original motivation, is optimal decisions are conditioned on models. And if the models are approximations, then so are the decisions. We're increasingly in this world where we are using, approximate models on large, complex data. I think it merits a reappraisal of Bayesian robustness. There was a lot of work of Bayesian robustness in the 80s. It really kind of tailored off. Almost all of the things we work on are approximate by design. So I think statisticians should be sensitive to decision stability. Thank you.
What is your recommendation regarding the choice of this lambda? Because it seems like quite a critical choice, right?
Yeah. So the neighborhood size, lambda, or the Kullback-Leibler, is a critical parameter. So what we have here is really just initially qualitative. Yeah. So what we suggest, our recommendation, is to play with lambda and explore these marginal distributions. Yeah. So as you play with lambda, you can look at what is the resulting change in the distribution of the local minimax, and you get a sense, well, if there's not a great difference between, say, using your standard model as the red distribution or using a model which is like, if nature is really in green, not your predicted state which is red, then you would choose a very different design. And so here I presented we're thinking of it as a qualitative exploratory approach. There are other approaches in econometrics. Hansen has ways of thinking about p-values around non-parametric tests. So you can think of, if I start off with my model here, if I moved away in Kullback-Leibler divergence and then generated samples and did a non-parametric test, how quickly, how far off would that p-value go? So if you move far away, of course, you'd say, oh, well, those distributions are very, very different. So it gives you that's one way of characterizing, what does a Kullback-Leibler divergence of 5.5 mean, is to try and turn that into, well, what would be the p-value under a non-parametric test to distinguish those two distributions. But I think it's an open issue.
This case is nice because you increase lambda, but you don't see much change. But imagine that by increasing lambda, the posterior change completely. When do you stop increasing lambda?
Well, I think the issue is that if you increase lambda slightly and the posterior changes completely, that's a time to reassess. You've learned something. Okay. Yeah. So this is what I kind of feel. Well, you've learned something. Like you need to maybe go back and think more carefully, or try and assess what is it that's leading to that kind of instability in the expected loss. But my sense is that you've learned something by that process. Hi,
Chris, Brett Efron wrote a paper recently. It's pretty simple, but what he was doing was, he said, okay, I want to take a Bayesian analysis, but then I want to bootstrap the thing and just have a look. And I'll add to that one of the things that's in the frequentist in regression, people do various diagnostics to see if the model fits. So what do you think about Efron's suggestion, which is obvious, but nevertheless, I find it quite appealing?
So I think there's some connections there with the Bayesian bootstrap. If you think about the Dirichlet process sampler is doing here is just kind of bootstrapping, in some sense, the weights, but doing a Bayesian bootstrap using a Dirichlet to resample the weights. I think the nice thing, well, of course, I kind of prefer this. I mean, one thing that we can say here is we can say something very strong formally about what that sample does. So if you bootstrap your weights using the Dirichlet, or if you reweight using the Dirichlet, we can say something very formally about what's the Kullback-Leibler divergence between the resulting sample, or the distribution of those samples, and the original model. But I mean, again, this idea of, you'll hear in this idea of people say, shake your data. yeah, by bootstrapping. Yeah, so people say, oh, you know, well, you should shake your data by subsampling and bootstrapping, you know, to kind of get a sense of variation. And so the analogous thing in Efron's approach and here is like shake the model as well, just and look, yeah, and see how stable things are.
Okay, let's thank Chris again.
Thank you.